This is a great set of problems. In my very humble opinion, you could teach students everything they need to know about slope, functions, input-output tables, all of this stuff using these 5 scenarios. Again, thinking deeper, not wider, I believe you could do the whole thing with these 5 items. These are good problems. So, let me show you how I would do it. Doesn't mean it's the best way, but this is what I would do. The first thing I would do is teach them, or first of all, I would provide them with some graphs, some coordinate planes like this one. You should be okay with just the first quadrant. You don't need a whole plane. Then here's the next thing I would do. I would teach them to write an if-then statement for each of these. So let me show you what I mean. In scenario A, it says that Kate runs for 6 miles per hour. Kate runs 6 miles per hour. She records the number of miles Y she runs in X minutes. So the first thing I would do is have them to write an if-then statement. If Kate runs 1 hour, and this is where I would put a box. If Kate runs blank, comma, then she will cover blank. Because once you get this together in this type of format, you have your independent and dependent variables already mapped out. Okay, there we go. So, whatever you put in this box with the if is the independent variable, and therefore it will go on the x-axis. Whatever follows then is the dependent variable, and it will go on the y-axis. So if you can get them to set up a sentence, you've got your axis labels. Okay, so let's plug in some variables here. If Kate runs 1 hour, that's my independent, my x value, then she will cover, about messed up, 6 miles. So I would probably have them to go ahead right here and build an input-output table. Depending on how experienced the students are, they may know how to do this already, but if they don't, this is a wonderful time to teach them. You can even throw in domain and range. I won't do that because I'm chasing rabbits, but this will work. So your x value is going to be the independent variable. The dependent is your y. That's just another way of saying independent, x and y. And here's the next thing you want to look for. I would have put this one last if I had written this set of choices, but you want a scale ratio. Now be aware that the scale ratio may or may not be the slope, and I'll show you what I mean by that. But in this case, we have 1 hour, 6 miles. Now you could write it as 6 over 1. That would be fine. But this is what will help you populate this table. But be careful. They said that they want the number of miles to be on the the y-axis. That's dependent. So this is going to be the number of miles. And the x-axis is going to be in terms of minutes. Now, they gave us the 1 hour, but we have to work with that in terms of minutes to graph it. So I'm going to change this 1 hour to be 60 minutes. And if I simplify that fraction, that means that she can run 10 minutes and cover 1 mile. Okay, and back to my input-output table. Let me go ahead and put in another line here. Because we know that X is our minutes. That's the one that she has control over. If I choose to run for this many minutes, this is the number of miles I will cover. So 10 minutes, 1 mile. 20 minutes, 2 miles. 30 minutes, 3 miles. You could also talk about this as a function because the scale factor doesn't change. It's 10 to 1 every single time you add a value. That's the definition of a function, or a definition of a function. I'm not going to graph all that, but I just wanted you to see it. So then I would come back to my graph and actually graph this set of data. So I have time in minutes, 10 minutes, 20 minutes, 30 minutes, 40 minutes, 50 minutes, 60 minutes. There's that hour that we were originally talking about. In 10 minutes, she covers 1 mile. Now, I would also stop and ask the students, if she doesn't run any minutes, does it make sense that she covers no miles? So technically, this graph is starting at origin. 20 minutes, 2 miles. 30 minutes, 3, 4, 5. I do like to go to 6 on this one because that's that hour that we started with, and that should be the 6 miles because they told us that in 6, to get 6 miles, she's going to have to run for an hour. The next thing I would do here is demonstrate that concept of rise over run. So you have rise 1, run 10, rise 1, run 10, rise 1, run 10, and so on. So let them see that those stairs are perfectly straight. They're perfectly even stairs. That's what slope is about. And then graph that linear function that is a positive linear function. Okay. All right. So this is not the choice we're looking for. This was, let me not put it there. This is choice A. And it's positive, so that's not going to help us. To me, that's the most difficult graph in this set. Okay, let's do B. So I'm going to start with an if-then statement. Let me go ahead and start that if. Well, I'll have to read it to know what if. A company sells an item for $12. Let X be the number of items sold and Y be the total sales. So if I sell one item, then I make $12. Okay, there is your independent variable. And here is your dependent variable. because your dependent variable depends on the number of items you sell. Your money is going to depend on how many items you're able to sell. So they want us to graph X be the number of items sold. So this is the number of items from 1, 2, 3, 4, 5, and 6. And then Y is the total sales. And we'll get that in just a second. But I also need to know that scale ratio. Help them to identify the scale ratio, where it costs $12. I like that 1 in the bottom because that will help me get my slope. $12 for one item. And as long as you have a 1 in either the numerator or the denominator, you're ready to graph. So $12 is the cost for one item. And then I would stop and say, okay, what if I sold 0 items? Then I would have $0. So the pattern holds even there. 2 items would be 24, because this one is scaled by 12s. Then 36. 4 items would be $48. 5 items would be $60. And 6 items would be $72. And again, you could draw those stair steps in there and show that if you needed to. But if you draw that linear function, you can see that it is going in the positive direction. So it is a positive slope. So B is not the scenario that I'm looking for. You could do a table of values there if you wanted. All right, here comes C. And C says, Brian is mountain biking up and down. Now that word down, in my opinion, is a distractor. They're trying to get us to hook onto that and say, oh, that down must mean negative. But you have to realize that Brian's biking and my graph are 2 separate things entirely. Just because Brian may be going down the mountain, that doesn't mean that my graph is going to go down. So they're 2 separate things. But he is keeping a constant speed, and that's important, of 10 miles per hour. Let X be the time spent mountain biking, and Y be the total distance biked. So here comes my if-then statement. If Brian X is the time spent, because this could be reversed, but they want us to use time as the X value. So if Brian bikes 1 hour, comma, then he will travel 10 miles. Okay, so here is the independent variable. Brian decides how much time he's going to bike. And depending on how much time he allows, that's the distance he will travel. So my independent variable, the number of hours that he chooses, let's say time in hours. And you might be thinking, well, don't I have to convert this one to minutes? And in this case, no, because this one doesn't talk about minutes at all. scenario A did. And then the dependent variable is going to be his total travel time. So if he bikes no hours, he travels no miles. Sorry, not his travel time, his travel distance. I had time on both axes. So no hours, no miles. 1 hour, and that's where I need my scale ratio. Of 1 hour to 10 miles. You could also write it the other way. Remember, ratios can be upended. However, if you want the slope, you need the rise on the top, which is the distance on the top, distance over hours. This would give you your slope. Okay. Let's see. 1 hour, 10 miles. 2 hours, 20 miles. 3 hours, 30 miles. 4, 5, 6, 40, 50, 60. So we have yet again that same graph. Now hopefully students would realize at this point I've drawn the same graph 3 times in a row. That means that all of them are similar. They're all positive slopes. So this is not the graph I want either. I mean, it's the graph I want, but it's not the answer to the question. So let's keep going. Here's the graph when we're ready. And here's the story. Reline that. All right, scenario D. Ted bought 100 shirts for $5 each. For 20 consecutive days, he returned 5 shirts a day and got his money back. Let X be the number of days Ted returned shirts, and Y be the total amount spent on the shirts. So let's go ahead and put the parameters down first. X is the number of days. And they say 20 consecutive days. I'm not going to draw out 20. We're going to go to 6 and then stop. But you could go all the way to 20 if you really wanted to do that. And then Y is the total amount spent on shirts. Now that word spent is important. Spent is another way of saying that it's not in Ted's pocket. Okay, so that's going to be my y-axis value. And we know this time that Ted, how do I explain this? We've got the number of days, we've got the dollars. The 100 is the thing that makes this one harder. Because that's it. We're working backwards from 100. We know that on day 1, Ted has 100 shirts. He has also spent $500 because 5 times 100 is 500. So he has $500 out of pocket on day 1. Do you see the difference here? Already, if I get this nailed down just as much as I have done here, already I can tell that this is different because we're starting up there at 500 and we're going to work backwards. So on day 2, okay, the first time he went back to the store, what did he do? He returned 5 shirts. So that's 5 times 5 is 25. So on day 2, he had $475 spent because he put $25 back in his pocket. On day 3, he was out of pocket $450 because remember, each one of these, what's happening right there? He is returning 5 shirts. And am I the only one who thinks Ted is just plain weird? This is one of the dumbest scenarios I've ever heard of, but I understand what they're getting at. So he returns 5 shirts. That's -5 times $5 each is -25. So each time he does this, that's another -25. So on day 4, he goes back again. He puts another $25 back in his pocket. On day 5, he goes back again, puts another $25 back in his pocket. You can see that negative slope building. So he's down to 400 at this point. Then on day 6, he takes back another 5 shirts, and he's down another 25 back in his pocket. So this time we are working backwards from a total. This is a negative slope. The rise over run thing still holds. With rise on this one, you drop 25 and you run 1. Drop 25, run 1. Drop 25, run 1. It's the dropping that makes the negative slope. So C is the answer. Now let me write an if-then for you, because that will also hold. If a day passes, then it's not returns 5 shirts, because remember what your y-axis is measuring. Ted puts $25 back in his pocket. Okay, there's the independent variable. Here's the dependent variable. So that if-then statement does hold true. Your scale ratio for this one is dollars to days. So he's getting a refund of $25 every day. This would be a good one, in my opinion, to do a table on. I think that would help maybe to clarify a little bit. This is just a tough one all around. Set up your input-output table. Remember, X is your independent variable. It is the input. And in this case, it's the number of days. Y is your dependent variable. It's the output. And in this case, it's the number of dollars spent, or the number of dollars out of pocket. So on day 1, or at the beginning of this mess, he had spent $500. On day 2, he had spent $475 because he brought back 5 shirts. On day 3, he brought back 5 more, so he'd only spent $450. On day 4, he brought back 5 more, so he only spent $425, and so on. Again, this is one of the dumbest scenarios I've ever heard, but I would be hard-pressed to come up with one that would make sense either, so I shouldn't be critical. D is the one we want. This is the choice, the negative slope. I will go ahead and do E, though, because that's another good example. All right. Last but not least, Jack had to slow down. Again, there's a distractor. Just because it says slow down doesn't mean the slope is negative, because Jack in his car and my graph are not in any way the same scenario. Jack had to slow down since the speed limit changed from 45 miles per hour to 25 miles per hour. Let X represent total driving time and Y total distance. Now, I'm assuming they want us to graph the change in speed. So I'm going to go ahead and find the scale ratio to start with. Of the change in speed. Because we could graph the 45, we could graph the 25, but since they're talking about a change, I'm assuming that's what they want us to do. So 45 minus 25 is going to be 20 miles per hour change. So you've got the ratio right there, 20 miles. Let me just do it that way. Per hour is 1 hour. And I'm assuming that's what they want us to graph. So the if-then statement would be something like this. If Jack drives, X is total driving time, so that's time. If Jack drives 1 hour, then he will travel 20 miles. Okay, that can translate simply, not simply, but it can translate into one of these tables. And the more you draw these, the more comfortable you get with the components of them. The independent, the input, is X. And in this case, X is total driving time. So it's time. The dependent is Y. And it is going to be distance. And so here is our scale ratio. We have 20 miles to 1 hour. So 2 miles would be 40. 3 miles would be 60. You see how those Y values are increasing? That would suggest to me a positive slope. 80, 100, 120. So when you're ready to graph this, they say to let X represent the total driving time. And I always, just for my own preference, it's completely just my preference, I like to put the label time in hours or time in minutes or time in seconds. It's just good practice, and it'll help you in science. And then Y is the total distance in miles. So if Jack drives 0 hours, he will travel 0 miles. If he travels 1 hour, he will travel 20 miles. Because remember, we're not worried about slowing down and speeding up. We're looking at that rate of change, that ratio of change. So 2 would put him at 40. And you see that old familiar pattern starting to emerge again of a positive slope. And that will continue as long as I want to sit here and do that. So it'll continue on to infinity, technically. As long as Jack wants to drive, that pattern will continue. And that is a positive slope, so it's not the one that we're looking for. E is a positive slope. I hope this has helped and has not made it more confusing. Just while I'm here, and just because of what we did before in the problems you sent me, let me go ahead and show you how to write the equation for that line, and also how to calculate slope actually from that line. So if you had this graph, you could pick 2 points on the graph. So 0, 0, and 120. And you can get your slope from those points. So I'm going to call this x1, y1, x2, y2. And here's the slope formula. Rise over run. One minus 0 equals 20 over 1, or 20. Now I want you to notice something here. You're going to love me right here. This fraction right there, the slope, is the same thing as this fraction, the scale ratio. As long as the denominator is a 1 on that scale ratio, that is your slope. Miles to hours, miles to hours. That is another way you can think about slope. So you can apply that slope formula right there. Now, if you want to write an equation for your line, as we did in some of those previous videos, here's how you would do that. You need the point slope formula. So you would have y sub 2 minus y sub 1. No, I'm sorry. I'm a fruitcake. It's not the right formula. It's slope-intercept. Y equals mx plus b. Okay, so we just found slope. We found that to be 20. So we just need to know where the y-intercept is for this graph. So look up here at your graph. You could solve for it by setting it equal to y, but you don't even have to do that, because right there, it's touching the y-axis at 0. So your formula, your line equation, is y equals 20x. So if they asked you to write an equation based on this graph, you could absolutely do that. The only other thing I could think of that they could ask you is what type of function it is. So if they put it in function notation, you would have f of x equals 20x. And it is linear. It's in a straight line. It has a positive slope because the 20 is positive. Also because it's going up. It's a positive slope. So they could ask that. I can't think of anything else. But think about all those skills that are all tied up right here in these 5 problems. This is a good set of problems and one that I would definitely hang on to. I hope I haven't made it worse. I know it's a lot to take in. But if I can help in any way further, let me know, and I sure will.